My name is Nicolas Rinaudo. I work for a Swedish company called Decoding, where we do a lot of online content moderation and machine learning. And I'm speaking with you this morning because I would like to talk about type classes, because I think they completely blew my mind when I finally understood them. And the purpose of this talk is for you to be able to answer the questions, what are type classes, how do they work, and what purpose do they serve? And the way I reached my own conclusions on type classes was by implementing my own CSV parsing and decoding library. So that's what we'll be doing this morning. We'll be going through some CSV, and hopefully by the end of it, you'll reach the same conclusions I did. So the first step is going to be parsing some CSV. Parsing is the act of taking some raw CSV data and turning it into some abstract in-memory representation that you can manipulate. Not yet a useful business type, necessarily, so that would be decoding, but parsing is just turning your data into something you can work with. And in the case of CSV, it worked like that. Your CSV is a list of rows, where each row is a list of cells, and each cell is a string. So what we're going to try to do is to write a function that goes from a string, that's the entire CSV, and turn it into our abstract syntax tree by first splitting on line breaks, then mapping into each row and splitting on commas. And if you run that input on our parse CSV method, you get the expected output, a list of string with the expected values, which is good. This is what we set out to do after all, but it's not great, is it? Because clearly this data is crying out to be decoded as list of ints. Those are all ints, so we don't actually want to work with strings. And this is the act of decoding, turning our AST into useful business types. So we're going to be decoding CSV now. And a fairly naive way of doing that would be to first parse the CSV into a list of cells, map into each row, map into each cell, and then turn each cell into an integer. And this works. If you run that, you get the expected output, which is good. But it's not very comfortable, is it? Because we have to be very aware of how our AST is built. We have to be very aware of how to parse the cells. It's not abstract enough. It's not comfortable to use. And so we will want to turn that into something a bit more abstract. And the usual strategy when you want to do that is to take your code, stick it into a function, and parameterize everything you can, just to see if any pattern emerges. So we'll do that. Here's our function, which takes a raw CSV as a string, returns it as a list of ints by running exactly the same code that we had before. We could probably turn that into parameters, though, by having a cell to int function as a term parameter and applying that into each cell. It's a nice step forward. And it looks here that we've taken all the term levels parameter things and put them in as parameters. But what about types? So this int thing, we do need to know there's a type, but we don't actually need to know what type it is, do we? Because we never use the fact that it's an int in the body of the function. So we could turn that into type parameter. And having done that, we can now call decode CSV and specify toInt, which is going to yield the expected result of a list of ints with the expected values. But we could also do it by asking for them to be parsed as floats. And that's going to yield a list of float with no additional work on our part. There's quite a big step forward here. We don't have to know how the data is structured. We just have to tell decode CSV how to parse a cell. But we don't need to know about the list of things. But it would be even nicer if I could just tell the compiler, well, this is a type I want to decode each cell as, and you work it out. I don't want to be bothered with it. And luckily, Scala has a mechanism for that. It's called implicits. And for people who are not yet familiar with it, it can be a bit intimidating, but I'm going to try to make it as simple as possible, because it's really not all that complex. Implicit resolution works as follows. When a function expects a parameter of type A, and that parameter is marked as implicit, and there exists a value of type A marked as implicit, then if the parameter isn't specified, the compiler will use that implicit value. which means that our printint of default int here, which unsurprisingly is going to print 2, is strictly equivalent to not specifying default int at all, which is going to be useful for us because if we have an implicit parameter of a type, we have an implicit value for that type, the compiler gets to stick it in there. So if we rewrite decode CSV to take an implicit decoding function, and that's the only modification we make, and we declare an implicit cell-to-int function, then we get to write decode CSV as follows. We just say, I want cells to be integers. The compiler is going to understand that to mean that he should look for an implicit cell-to-int, find str2int, and yield the expected output. And it's strictly equivalent to not at all specifying str2int, which is quite convenient. So at this point, let's take stock. What have we done? Sorry, I skipped ahead a bit. Yep, if you know about implicits, you know that we've done something a bit unfortunate here. We have run into implicit conversions. One wrinkle of the implicit resolution system is when a compiler finds a type A, where it expects a type B, but there exists an implicit function from A to B in scope, then that function will be applied silently. Which means that here, add one of str2int of the string 123 yields the int 124, which makes sense, but is strictly equivalent to add one of the string 123, which can be a bit confusing. It can be a bit surprising. Whether or not that's a good feature is up for debate. There certainly are a lot of debates on the matter, but here, that's a bit out of scope. We didn't mean to do that, did we? This is a bit of a side effect, isn't it? We didn't want to do that, and yet it happens. And we would like this not to happen. So how could we do that? Well, the thing that triggered implicit conversion being the act of turning one type into another implicitly. Well, this was triggered by implicit functions, right? It's because we have an implicit string to int in scope. So we need to rewrite our cell decoding function in such a way that it doesn't have type function. We could do it as follows. We could have a trait cell decoder of A, which exposes a decode method, which given a cell yields an A. And that is, in all but type, a function. It doesn't have type A, cell to A, but it does, it's just a wrapper for the decode function. Given that, we're going to need to create a bunch of them. So let's write a creation helper by opening the companion object and declaring a from function that yields a cell decoder of A by taking a cell to A and sticking that into the decode function. And now we can write as many as we want, such as this one's cell decoder of int by specifying to int, cell decoder of float by specifying to float, cell decoder of string by not actually doing anything because we already have strings, and cell decoder of boolean by specifying to boolean. And having done all this work, we can now update decode CSV to take a cell decoder rather than a function from cell to A, use that cell decoder on each cell, and now I can write decode CSV of int, which is not going to trigger, which is going to cause the compiler to look for an implicit cell decoder of int, find one, generate the expected output, which is strictly equivalent to not specifying at all this cell decoder. And that also works for floats in exactly the same way, because it's going to look for a cell decoder of float. We have declared one, and that's going to work out. But again, we don't have to specify the decoder explicitly. So if we take stock now, what have we achieved? We have made decode CSV polymorphic by using, first, parametric polymorphism, because we have cell decoder, which has a type parameter, decode CSV, which has a type parameter, and is this type parameter match, then we can stick one into the other, and it all works out. And we've also used implicit resolution so that we don't have to take our to specify our cell decoder explicitly. This pattern is known as a type class. Now, type classes are very often associated with functional programming. They were, after all, invented in Haskell, and they don't occur in many languages, and most of them functional. But could we have done the same thing with object-oriented programming? Is this really something that's specific to functional programming? Well, let's try first to do it in Java. The following slides might look a bit like I'm trying to troll Java. I'm not. I've written them as best I could in Java, but my Java is very rusty. And I'm very open to the idea that there's a better way of writing the Java code I'm going to show you. If there is, please let me know in Slack later so that I can update the slides, because they're a bit shameful, you'll see. So first, when you work with OOP, your main vector for polymorphism is subclassing, isn't it? So this is how you do it. You'd use an interface, decodable from cell, which exposes the decode cell method that from a string yields an A. And then you'd write decode CSV, which is that's the slide I was talking about. It's a bit messy, but I'll walk you through it. Decode CSV takes a CSV, so raw CSV as a string, as we've done so far, returns a list of A, where A is a subtype of decodable from cell. And it does so by first passing the CSV, mapping onto each row, and then mapping onto each cell, and encoding the decode function. But this is where we hit a bit of a problem, isn't it? The decode function, which is from string to A, how do we write it? The only thing that kind of looks like that we have available to us at this point is A is a decodable from cell, so decodable from cell dot decode cell. But we can't really use that, can we? Because with subclassing, you need to have a value in order to be able to call the method, don't you? We need to have an A in order to be able to call decode from cell, which we don't actually have an A. We're trying to produce one. We don't have one to work with, so we can't really express that. This is fairly important, because that is one of the main differences between type classes and subclassing. Type classes decorrelate the behaviors from the values. You can have the behaviors, cell decoder, on the one hand, and the value on the other, and you can use one or the other or both. It's not a problem. They're not linked. Whereas in subclassing, well, the values and the behaviors are correlated. You need to have an object in order to be able to call its methods. So we're kind of stuck here, but if type classes are simply passing a dictionary of behaviors around, then what's to stop us from doing that directly in OOP? And nothing, really. We could declare cell decoder just like we did in Scala, which has a decode method, takes a string and returns an A. And then we get to rewrite decode CSV by taking a cell decoder, and then the decode function write itself is just a proxy to cell decoder.decode. Having done that, we can declare a cell decoder of integer, which is just %. And then if we decode the following input by explicitly specifying our dictionary of behaviors, then we get the expected output. So this is very similar to what we've done in Scala. The main difference here is just in Java, we had to be explicit about the dictionary of behaviors. And this is actually a pattern that you will find in the Java standard library. For example, when you want to sort list of elements, you have two ways of going about it. The first one is to have a list of type that is subtype of comparable, and then it all works it out. But you could also explicitly specify a comparator, which is essentially a type class for comparing two elements of a given type. So the takeaway here is that subclassing requires values where type classes don't. Type classes decorrelate values and behaviors. So that makes them at least slightly more flexible. But on the other hand, they really look a lot like they might merely be syntactic sugar for passing explicit dictionaries of behaviors. And while that might be true, it's not a bad intuition to have. I want to show you how powerful this syntactic sugar can get by showing you how type classes compose implicitly. And in order to do that, I would like you to consider the following CSV file. The first column is integers, and the second one is strings. And we get a bit stuck here, don't we? Because we would really like to decode that CSV file as a list of tuple in string. But we can't do that. What we have at the moment is how to decode a CSV file into a list of A. We decode the cells, not the rows. We don't have that functionality yet. But we have spent a fair amount of time now designing a way of decoding cells into something. Why don't we apply the same to rows by declaring a RowDecoder type class, which exposes a decode method that goes from row to A? Again, we'll need to create a bunch, so let's write some creation helpers by opening the companion object, exposing a from method that returns a RowDecoder of A by taking a function from row to A and sticking it into the decode function. Now, we have RowDecoder. We need to update Decode CSV to use it. So Decode CSV now takes a RowDecoder of A and has been modified to map into rows and decode them, rather than to map into rows, then into cells and decoding them. And once we've decoded a row, we just return the whole thing as a list of A's. So if we manage to exhibit an implicit row decoder of tuple in string, then we'll be able to decode the CSV I showed you the way we want to. And it's actually fairly easy to write. Here's our row decoder of tuple in string. You write that by taking a row, extracting the first cell as an int, the second one as a string, and sticking the whole thing into a tuple. This is nice. This will work. It's still slightly disappointing, isn't it? Because we've just designed cell decoder. We've been extolling its virtues. We've been saying how great it is, and now we're not using it at all, and we're hand passing everything again. I'd really like to be able to use our cell decoders here. But, well, the first step is going to be to use them manually like that, which is slightly better, but still not great. I would like them to be passed as parameters to tuple decoders so that I can change the behavior of it. Hopefully, I could even make them into implicit parameters if possible. But the problem, of course, is that tuple decoder is a val, and values famously don't take parameters, implicit or otherwise. Luckily, there's another wrinkle in the implicit resolution mechanism. When a compiler looks for an implicit value of type A, and here we're looking for a float, and finds an implicit function that returns an A, that it can call, and can the compiler get float here? Well, getFloat takes an implicit double, but there is an implicit double in scope, so the compiler can take that implicit value and stick it into getFloat, and then the compiler will use that function. So our entire code is equivalent to printFloat of getFloat of the full double, which unsurprisingly prints 3.0. It's strictly equivalent to not specifying anything at all. So if you make your function implicit and it only takes implicit parameters, then the compiler can work everything out and stick everything where it belongs and generate a lot of code for you. This allows us to rewrite tuple decoder to be a def and to take cell decoder instances rather than use explicitly a hard-coded cell decoder of int and string. They're both implicit, but we can go further because these types here, as before, we don't use the fact that we're working with an int and a string, do we? We need to know the types, but we don't need them to be hardwired to int and string. We could turn them into type parameters as follows. And now this allows us to say, given a cell decoder of A and a cell decoder of B, I can exhibit a row decoder of tuple A, B. And we're done. Now, if I have the following input, I can call decode CSV and say, I want everything to be decoded as tuple in string. And the compiler is going to look for a row decoder of the right type, find tuple decoder, realize that it needs a couple more parameters fulfilled. And the first one, cell decoder of int. Well, we have int cell decoder, don't we? Same for cell decoder of string. We have everything we need. So the compiler is going to stick everything there. It's going to compile it, run it, and generate the expected output. But the good thing is, it's strictly equivalent to not doing any of that hard work. Now, if you've been paying attention, you realize that we have lost a feature by doing that. We can't decode that anymore because now we need a row decoder. Decode CSV doesn't take cell decoders anymore, but row decoders. So this we'd like to decode as a list of int, but we don't have a row decoder of list of int. It's fairly easy to write though. For any A that has a cell decoder, I can expose a row decoder of list of A by simply mapping onto each cell and applying the cell decoder. Which, given the following input, I can now decode CSV and ask, I want everything to be a list of int. And the compiler is going to look for a row decoder of list, find one. This still needs another parameter fulfilled. It needs to know how to decode cells into int. It's going to find int cell decoder, compile, run, generate the expected output. But again, this is all works that we don't have to do because the compiler does it for us through the magic of implicit resolution. We could go further. This CSV file, for example, fairly common. The first cell is an int, and sometimes not there at all, which we want to decode as tuple option of int string, don't we? And this, well, is not very hard. because I can have an optional cell decoder of A. For any A that has a cell decoder, I can expose a cell decoder of option of A by checking if the cell is empty. If it is, then we return a none. Otherwise, we decode the cell and stick into a sum and return that. And that's it. Now, given the following input, I can ask for my CSV to be decoded as tuple option of int string. And the compiler is going to work everything out. It's going to need a RowDecoder, find tuple decoder, then need a cell decoder of option of int, which is going to find, still needs to know about how to decode ints. It's going to find int cell decoder, and cell decoder of string is also fulfilled fairly easily. And all this is going to compile and yield the expected output. But again, it's work that we don't have to do, which is the best kind of work. It gets even crazier because CSV is a bad format. Here we have a cell that's sometimes an integer, sometimes a Boolean, which happens a lot more than you'd expect. And that is something we'd like to decode as an either, well, tuple of either int Boolean string. And writing a cell decoder of either is straightforward. Given an A that has a cell decoder and a B that also has a cell decoder, then I can produce a cell decoder of either AB by attempting to decode the cell as an A and sticking that into a left. And if that doesn't work, then decoding it as a B and sticking that into a right. And now, with the input I showed you before, I can call decode CSV with the right type parameter, and the compiler is going to work it out step by step. RowDecoder is a tuple decoder, needs a few more implicit parameters. It's going to work them out one at a time, do all that work for us so that we don't have to. And in the end, the compiler is going to generate all that, which compiles, runs, but is really something we don't have to do because the compiler will do it for us. Now, I'm going to go a bit nuts here, but I'm not going to do all of the steps because it would take ages. But this CSV file, which looks innocent to begin with, but the first cell is sometimes an int, sometimes a Boolean. Second one is sometimes a string, sometimes not there at all. And just to be a bit perverse, I want to decode that as a list, not as a tuple. So the following input should be decoded as this type that I'm, for obvious reason, not going to read out loud. And we don't have any further work to do. We've already done all the work. Implicit composition is going to sort it out for us. The compiler is going to be busy for a bit and realize that it needs to generate all that code in order for these things to work. And that generates the expected output. But it's equivalent to not doing any of it. And that was a lot of code that we didn't have to write, which is really quite nice, isn't it? I mean, what we've seen is, yes, type classes are strictly syntactic sugar over explicit dictionaries of behaviors. Because there isn't one example I've given you in which we could not have done the work manually by combining all these instances by hand. So they are syntactic sugar. It's just a compiler working out things for us that we could do by hand. But they're so very nice. It's such a very nice bit of syntactic sugar, isn't it? Because of all the work it does for us. In fact, it's such a nice bit of syntactic sugar. It's so important that if you look at the Scala language, it's got a lot of syntax to go with it to help us make it even nicer. And it's going to evolve to give us even more syntax. So I'm going to show you what we have and some of what we'll be getting in the near future. Well, near, I mean, dotty, who knows? Right, so first, this bit here, the designers of the language decided that that was too much to write, really too much work altogether. So they decided to create the context-bound syntax, which works as follows. This reads, decode CSV takes an A type parameter, which also takes an implicit parameter of type RowDecoder of A, which we don't need to name. It doesn't actually have a name, which is a problem slightly because we can't call it directly because it doesn't have a name. So we have to summon it with the following slightly unpleasant syntax. I personally don't like it very much, but that's all right though, because an idiom in the Scala language when you work with type classes is to create in the RowDecoder, in the companion object, to create an apply method that for any type A that has a RowDecoder, return that value, which allows us to rewrite decode CSV as follows. And that syntax, on the other hand, I find quite pleasant. It might be my Java past, but this looks like a static method called an abstract type. And it looks quite nice. Good enough for me, at least, but not for everyone. And a lot of people like to use what's known as extension methods, which rely on implicit conversion. So we have an implicit conversion, which, given a row and an A that has a row decoder, then I will add the decode row method to row that returns an A by decoding the row, which allows us to rewrite decode CSV like that. And this is actually really quite nice. It reads, it's very obvious when you read that code what it's trying to do and how it works. The only downside, of course, is that the syntax for declaring the extension methods wasn't great. It was all very boilerplatey, and it's not even the same class as a type class, which kind of violates the principle of locality, doesn't it? So that's not extraordinarily pleasant, but luckily, the designers of the language have us covered, because in Scala 3, we're going to get dedicated syntax for an extension method, which works as follows. For a row, I add a decoder method, which returns an A by decoding the row. And since we're already inside of a type class instance, inside of RowDecoder of A, we know how to do that. We already have it. And through the magic of implicit resolution, everything is always going to work out. And the syntax is very, very, very pleasant here, I find. So what we've done, we have seen that type classes, they already have a fair amount of dedicated syntax. They're already a fairly important part of the Scala language. And they're about to get a lot more as well in Dotty. If you've read the tutorials on Dotty, you see that type classes are front and center. So they really are a construct that we should all get familiar with and learn how to use, because they're going to get more and more important for the Scala language. Now, in closing, if there's just the one slide that you need to remember, it's this one, the answers to the question I asked in the introduction when I said I would like you to understand what type classes are, how they work, and what purpose they serve. Well, type classes are simply a clever use of parametric polymorphism and implicit resolution. They're a very convenient syntactic sugar, but mostly they're used to generate a lot of code, for the compiler to generate a lot of code, so that you don't have to. And I hope that convinced you that type classes were very useful. And usually at this point, this is where I'd ask, does anybody have any question? But in talks about type classes, this is always a place where somebody's going to go, but Haskell though. You know the kind of person, the Haskell kind of person, who's going to say, with reason, Haskell has type classes. Haskell invented type classes. We are the root of the whole concept. And we have a law that is absolute, which is a law of uniqueness. Unicity, uniqueness, which says that for any given type class and any given type, there can only be one single instance of that type class for that type. Scala doesn't have that at all. We don't enforce it at all. In fact, Scala has resolution rules, priority rules, so that when it finds two instances, distinct instances of a type class for a given type, then it has rule to decide which one to use. Haskell has global uniqueness and is going to refuse to compile. This can be an important feature to have. If you imagine, for example, a set which is an ordered collection of unique values. Traditionally, this is implemented as a binary search tree. And in order for binary search trees to work, you need to be able to compare values that you stick in there, which is achieved through the ORD type class. And in Haskell, you never have to think about it, because if you have a set of events, then you know you're always going to get the same sort order for integers because of global uniqueness. In Scala, you don't actually know that, because they're locally coherent, but not globally. So you might have a set, on the one hand, set of ints, and another set of ints, and both of them might have been initialized with a different instance of the ORD type class. So when you try to merge them, you might be using different orders, and you might end up violating some fairly important invariants. So this is a very valid argument to say Scala does not actually have type classes, because type classes in Scala don't follow the law of global uniqueness. Unfortunately, neither does Haskell. which I intend to show quickly. Haskell. Here, I declared a Boolean, data type Boolean, which can be either true or false. And if you open a first module, EMPL1, in which I declare an order for Boolean, which basically says that true is more than false. And then declare an inst method that takes a Boolean and a set of Boolean and inserts that Boolean in a set by using the ORD Boolean instance we've just written. Then I do a second module where the only real difference is that now the order is swapped. Now true is greater than false. And then I had inst prime, which is the same as ints, except it's going to use a different instance for order of Boolean. And having done all that, I can now write a main program which opens both modules, then create a set of Boolean by inserting t twice. And first, the very shocking thing is this all compiles. It really shouldn't, should it? Because Haskell has global uniqueness, doesn't it? Clearly it doesn't. And the thing is, I have added t twice in the same set. That shouldn't do anything, should it? It should be equivalent to only inserting it once. But if you go ahead and print test, then you get this monstrosity. You get a set with the same value in it twice. So Haskell doesn't really have global uniqueness, does it? It kind of does through convention, because in Haskell, it's very, very bad form to do what I just did. But the compiler completely accepts it. And saying that Haskell has global uniqueness is like saying Scala doesn't have nulls. We do have nulls. We choose not to use them, mostly, but we have them. The compiler will not complain if you use nulls. So the argument that I hear all the time that Scala doesn't have proper type classes because it doesn't follow the law of global uniqueness, if that's the only argument that we have, then really neither does Haskell. And now that I've done my bit of troll, because really it was quite a bit of fun, does anybody have any question?
Now I didn't see any questions. I'm afraid you were too clear in your talk.
Okay.
Yeah. One takeaway: don't break languages like you did with Haskell. If anyone will have some questions but was afraid to ask in a YouTube chat, please follow to the Zoom channel for the longer Q&A sessions. And please also give some round of applause on the YouTube chat.